All right, welcome back again, everybody. Today we're going to be doing section 5.3. We're going to talk about some properties of the trigonometric functions. In the last section, we got the actual trigonometric functions themselves: sine, cosine, tangent, cosecant, secant, and cotangent. In this section, we're going to talk about some of their properties. And then the next section, we'll actually review some graphing techniques before we start to look at the graphs of these functions. So we haven't seen the graphs yet, but we will, and we'll make good sense of the graphs too. But first, we got to talk about some basic properties. So let me get the slides pulled up. There we go. And let's take a look at the overview. So we're going to talk about periodicity, which we've actually already seen, and we saw it in the last section intimately, and we'll see it again in this section. Then we'll talk about some of the fundamental identities, and then we'll talk about symmetry. Here we go. So what is periodicity to start? So we say that a function is periodic if there is a non-zero number p such that f of theta plus p is equal to f of theta. So more specifically, what we're saying is that if you take your angle theta and you add some value to it, and you end up back, or I should say this, we're saying this: if you take your angle theta and you add p to it, that's the same thing as just starting with theta itself. So in particular, the outputs of these functions are the same. The outputs of the functions, right? So this is the output of the function when you put in theta plus p, and this is the output of the function when you put in theta. And we say that a function is periodic if those two outputs are the same for some non-zero number p, non-zero number p. And the number p itself is called the period of the function, and we say that f is p periodic for whatever that number p is. Yeah, so in other words, the function values repeat themselves every p units. And graphically, this means that the graph of f repeats every p units. And so we'll see this when we look at the graphs in section 5.4. All right, so we know what sine and cosine are now, and because they're defined as the vertical and horizontal displacement of a point on the circle, right? Point on the circle, determined by theta, both functions are periodic. And we kind of saw that when I was drawing the lines in the previous lecture, right? It basically goes up and down, left and right, left and right. That's periodicity. That's periodicity, and it's related to the fact that the thing is going around and around the circle. Right, round and around the circle. So in particular, sine and cosine are 2 pi periodic because the location of the point P just repeats every 2 pi radians. And this is something we saw last time too. So if we want to write that more specifically, we say this: sine of theta plus any integer multiple of 2 pi will be the same as sine of theta. And cosine of theta plus any integer multiple of 2 pi will be the same as cosine of theta, because these functions are 2 pi periodic. That's the idea. In fact, all 6 of the trigonometric functions exhibit some periodicity precisely because they're defined in terms of sine and cosine. So that's one of the reasons why I keep emphasizing that if you can grasp sine and cosine really well, then you can grasp tangent and cosecant and secant and cotangent just as well. You just have to make sure you're comfortable with sine and cosine. Okay, so if you want to get more specific, we can say this. These are the periods of these functions. So sine and cosine and cosecant and secant are all 2 pi periodic, but tangent and cotangent are pi periodic. So that's one thing to take note of. The short answer is that tangent has a period of pi, and so that's why cotangent does as well. We'll see more why that's true when we start to look at the graphs, but algebraically it's this. If you do any integer multiple of pi and you plug that in, or sorry, you add that to theta, you're just going to get the same tangent value at that point. There you go. All right, so this one, we actually had practice with this on the last section. So let's try to find the exact value of sine 17 pi over 4, cosine 5 pi, and tangent 5 pi over 4. So for this one, now that we've done it a couple times in the last section, I want you to try to do it on your own first, and then we'll do it together a little more quickly than last time. All right? So think about it and try it on your own right now. All right, now let's try to do it together. Here we go. Just like we did in the previous section, we're going to mod out by 2 pi. So first, let's do this one. Okay, we're looking at the angle 17 pi over 4, which is the same as 17/4 of pi. Let's see, 17 divided by 4 is 4 1/4 pies. Okay, so what do? Draw my unit circle. I'm going to go around 4 times. So 1, 2, 3, 4. Or sorry, I should say around 4 times pi, right? So 1 pi, 2 pi, 3 pi, 4 pi, and then 1/4 pi. So we're right there. Just like last time, this is going to be a 45, 45, 90 triangle. So we get that sine of 17 pi over 4 is equal to root 2 over 2. Done. Not too bad, right? So hopefully you're getting a little quicker at these now because you realize you just got to do division and then count. Just appeal to counting when you can, right? All right, so let's do the next one. Cosine of 5 pi. Well, 5 pi, we're going to go around 5 times, but it's just an integer multiple of pi. So we're going to land at either pi, or we're going to land at either pi or 2 pi, one of the two. Let's see. So 1, 2, 3, 4, 5. There we go. So we're looking like this. Oops. All right, what's cosine of this angle? This is the angle pi. Cosine of pi is -1. All right, horizontal displacement is -1. All right, what about tangent of 5 pi over 4? Erase this right here. 5 pi over 4. Same kind of thing. 5 pi over 4, that's 1 1/4 pies. 1 1/4 pies. So you're going to go a full pi and then 1/4 pi, and you'll end up down here. This is going to be a 45, 45, 90 triangle. Root 2 over 2. Root 2 over 2. But now, because it's in the third quadrant there, these are going to be negative valued. Now we know what sine and cosine are. We can find tangent. We get, maybe I'll cut through it a little bit. We're going to get this. Tangent of 5 pi over 4 is going to be negative root 2 over 2 over negative root 2 over 2, which is 1. And then it's always good to do a little check, right? What am I saying when I write this down? What does that really mean? Tangent of 5 pi over 4 is 1? That means the slope of that line is 1. Does that make sense when we look at the picture? Think about it for a minute and see if it makes sense that we would get a slope of 1. Yeah, that's right, it does, right? When you look at this line, that line's got a slope of 1. This is actually just the line y equals x, the 45-degree line, the pi over 4 line. Now it all makes sense. Okay, this is just all the details, so if you want to read through this on your own, you can. All the details of what we just did. Now let's talk about some identities. So, well, actually, one thing I'll mention is that this is going to be a much quicker lecture because we got the big ideas in the last one. But there are some fundamental identities that we're going to start with. There are actually dozens and dozens of these identities that we're going to learn throughout the class, but there are only a handful that you should memorize. There's only a handful you should memorize, and I'll be very, very clear about which ones you should memorize. The rest of them, I'll just give them to you if you're taking the test, because there's just so many of these identities, just so many. And there's no way to memorize them all comfortably, and there's no way to keep them all in order in your head comfortably. But there is a handful of them, in particular, I'd say 6, 7, or 8 maybe, that you want to have memorized. And I'll emphasize them as we go along, but this is one of them. This is one of the identities that you really, really do want to memorize. This is called the Pythagorean identity. The Pythagorean identity. And maybe you can kind of see why. This says cosine squared theta plus sine squared theta equals 1. So one thing, I realize I mentioned it on a later slide, but not this one. Do I mention it here? Yes, okay, there we go. So let me cut to this slide really quick. It's convention to write sine theta squared as sine squared theta. And the same thing for cosine and tangent, cosecant, secant, cotangent, etc. The reason is purely notational. It's purely for elegance. It's just because it avoids cluttering up expressions a lot. Because when you start to have a ton of parentheses flying around, which we will, it's nice to not have to include all of them. So don't let this confuse you or trip you up, but quite literally, if you see sine squared theta, it means sine of theta squared. If you see cosine squared theta, it means cosine theta squared. If you see tan squared theta, it means tangent of theta squared, and so on. That's really all it is. It's just a notational choice. And yeah, like I say here in the second point, this identity is called the Pythagorean identity precisely because x squared plus y squared equals 1 is the Pythagorean theorem. That's how we got this result. That's the equation of the circle, which it comes from the Pythagorean theorem, which comes from those right triangles. So it's all intimately connected. It's all intimately connected as long as you can remember the big picture of the unit circle and those special right triangles. That's it. All right. So let's prove this identity. The proof is very straightforward. The proof is like 1 or 2 lines. There you go. So any point x comma y on the circle, we know satisfies this equation. By definition, by definition, cosine is the horizontal displacement and sine is the vertical displacement. So we can quite literally just substitute in x and y, or I should say substitute in cosine and sine for x and y respectively, and we get this. That's it. There you go. That's the proof. All done. Let's see another one. So this is another identity, and this is the one that I call I tan in a second. And the reason I call it that is because one of my previous students years ago told me this mnemonic for remembering this identity because I had never heard it before. And he blurted it out, and I fell in love with it immediately. It's a great mnemonic to remember this identity. The mnemonic is I tan in a second. And what's the identity? It's 1 plus tangent squared theta equals secant squared theta. I tan in a second. You just got to remember to square the tangent and the secant. Okay, now let's see the proof. The proof is also remarkably quick. We're going to start with the Pythagorean identity. There we go. And we're just going to divide both sides by cosine squared. Divide both sides by cosine squared. There we go. Cosine squared over cosine squared is 1. Sine squared over cosine squared, that's just tangent. That's tangent squared, right? Sine over cosine is tangent. So this becomes tangent squared. And then 1 over cosine squared, that's just secant squared. By definition, right? What's secant? Secant is 1 over cosine. So 1 over cosine squared is secant squared. And there we go. That's the proof. All right. Then the last one. This one is I cotan in a cosecant. So just like we had I tan in a second for the last identity, it turns out there's another one that's related. It's 1 plus cotangent squared equals cosecant squared. There you go. What's the proof? The proof is also remarkably quick. You start with the Pythagorean identity again. There you go. Divide both sides by sine squared instead. So you divide both sides by sine squared. Well, like we had seen before, cosine theta over sine theta, that's cotangent. So this is cotangent squared. Sine squared over sine squared is 1. And 1 over sine squared, well, 1 over sine is cosecant. So 1 over sine squared is cosecant squared. And there we go. Ta-da! That's it. I cotan in a cosecant. All right. So these are 3 identities that you must memorize. You really, really need to memorize these ones. You will use them extensively in Calc 1. You'll use them in Calc 2. Actually, I'll say you'll use them in Calc 1. You will use them a ton in Calc 2. So this is my warning to you from the past to your future, basically saying memorize these identities. Get to know them now. Make sense of them now. Get comfortable with them now, because then when you're in Calc 1 and Calc 2, you'll be like, oh, I got this. You won't have to like memorize them then and relearn about them then. All right? So there you go. Learn about them right now. Okay, let's do an example. Let's find the exact value of this expression. Oof, this expression looks kind of like a beast. Take a moment, look at this expression, see if you can make sense of it, and then see if you can find the exact value. Then we'll do it together. All right, now try to write something down. See if you can make sense of something written there and get it started. All right, now let's try to do it together. For one, since we've just seen this new notation, it might help to write it in notation that's a little more familiar. So if you need to do this step, please do it. It's not wrong to do it. But sometimes when stuff gets a little bit funky, you have to use parentheses because parentheses are your friends, and parentheses can help you keep things grouped the way that you want them to. So when I look at this, I see this as sine of pi over 12 squared, sine of pi over 12 squared. And then here, I see this as 1 over secant pi over 12 squared. Okay, so now maybe you can actually see, this is one of the reasons we tend not to include all of these extra parentheses. Let me do this here instead. Um, pi over 12 parentheses squared. This is why we like to use that more cleaner notation, but in this case, it might make things a little bit easier to see. So we've got sine of pi over 12 squared, and then we have 1 over secant squared. But what is secant? I remember secant is 1 over cosine. So this is 1 over cosine pi over 12 squared. So this is going to be sine of pi over 12 squared plus cosine of pi over 12 squared. But check this out. This is sine of an angle squared plus cosine of an angle squared, right? That's the Pythagorean identity. This is 1. This is equal to 1 because you've got sine squared plus cosine squared. So the answer is 1. That's what it is. The value is 1 by the Pythagorean identity. And that's it. That's it. So this is a lot of what you'll see in this course with these identities. It's going to be a lot of manipulating these expressions and finding equivalent forms of them that may or may not be simpler. So this is an example of what you'll see a lot more later in the course. Okay, now let's try this one. So think about this one on your own, and then we'll try it together. So start by pondering it to yourself, maybe say some things out loud, and then try to work on it on your own, okay? All right. Now, one thing I want to remind you is try to say some stuff out loud too. I realize I haven't been throwing this up enough. I've been going straight to like the writing part, but saying things out loud, even if you're alone, can really help your brain process stuff. Just talk to yourself, or you can talk to your dog, or the wall, or your cat, or your friend, but saying stuff out loud can help. Okay, now let's try it together. Let's see if we can make sense of it. It says, given that sine of theta is 1/3 and cosine theta is 0, find the exact value of the remaining trigonometric functions. Okay, so it doesn't even mention that we're using a unit circle or anything like that. So we just know that sine is 1/3. All right, sine is 1/3. Well, what did we know? We remember in the last bit, the last section, we knew that sine of theta was equal to y over r, right? So if you had a circle that wasn't necessarily radius 1, It would be y over r, vertical displacement divided by the radius. So what we know is that this is also equal to 1/3. So now we can just do a direct comparison. If y over r is equal to 1/3, this tells us that y is equal to 1 and r is equal to 3. There we go. Okay, so now we know what r is. We can figure out what cosine is, because what's cosine? Cosine theta was x over r, right? X over r. But then how are we going to find x? That's a good question. Let me start with this. Okay, we're going to have x over 3, but what is x going to be? How could we do it? What do you think? Right, the Pythagorean identity, right? So we know what y is, we know what r is, we just need to solve for x. And we also know that x squared plus y squared equals r squared. So kind of filling this in, we're going to get x squared equals 1, oops, sorry, plus 1 squared equals 3 squared. So x squared plus 1 equals 9. So x equals the plus or minus square root of 8. And then maybe I'll simplify that a bit. X equals plus or minus 2 root 2, just like so. And there we go. So now we just need to know if it's the negative or the positive one. Remember, whenever you take a square root, you must include a plus minus. Then you can toss out a case based on the situation. So here, how do we know which one to pick? What do you think? It's going to be the negative one. That's right. How do we know that? We're given that cosine of theta is less than 0. But we know that cosine is basically the horizontal displacement scaled by the radius, right? So we know immediately that we're going to have to pick the negative one. We're going to have to pick the negative one because cosine is less than 0. So that tells us that x, oops, let me just do this. X is going to be negative root 2 over 2. Negative root 2 over 2. Okay, and that's all we needed. So wait, if x is negative root 2 over 2, then that means that cosine is what? Negative root 2, oops, negative 2 root 2 over 3. Yes. All right. So now we've got sine, we've got cosine, we can find tangent, we can find cosecant, we can find secant, we can find cotangent, we can find all of them. All we needed to start was sine and cosine. So here we go. Oh, this is me just saying what I did. There you go. Pythagorean theorem or the Pythagorean identity. There we go. So we had this. This was given. This is what we concluded with our calculations. Once we have those two values, we can find tangent. Just do y over x. 1 over negative 2 root 2. To find cosecant, do r over y. To find secant, do r over x. And to find cotangent, do x over y. There we go. And that's it. That's the whole idea. So once you get sine and cosine, everything really does just kind of fall right out. All right, so that's it for identities for now. The next thing we're going to talk about is evenness and oddness. So there are these functions that are called even and odd functions. It's a very specific property that can be very, very helpful depending on the context. So we say this, a function is even if and only if f of negative theta equals f of theta for every input theta. Let me emphasize this right here. So intuitively what this means is if you change the sign of the input, it does not affect the output at all. That's what it's saying. So if you change theta to a negative angle instead, that's not going to change the output of the function. That's what it means to be even. An even function has that property. A function is odd if it does have an influence when you change the sign of the input. So a function is odd if f of negative theta equals negative f of theta. So what this says is, hey, if you change the sign of the input, it changes the sign of the output. That's an odd function. We say that's an odd function. Graphically, do I say it on this slide? I think I waited because we'll talk about that in the next section. Let me double check. Yeah. So we can see this on the graph as well, and we'll see it in section 5.4, but even functions are symmetric about the y-axis, as it turns out. Even functions are symmetric about the y-axis. Odd functions are symmetric about the origin, for example. But we'll explore that later in the next section. For now, the big idea is that if you change the sign of the input, does that change the sign of the output or not? If it doesn't change the sign of the output at all, you've got an even function. If it makes the sign of the output the opposite, you've got an odd function. So altogether, for our trigonometric functions, we get this. Cosine and secant are even functions, and then the rest of them are odd functions. There we go. So what I say, cosine and secant? Yeah, so odd function, odd function, odd function, odd function, even function, even function. And we're going to prove one of these, but if you want to make sense of why this is happening, guess what you're going to use? Think about it for a minute. What do you think I'm going to say? That's right, the unit circle. If you want to prove any of these things, you start by just looking at the unit circle, looking at the definition of sine and cosine, and these results fall out immediately. So let's check it out. Here's the proof that, oops, sorry, I wanted to say we're going to prove this one. We're going to prove that cosine is an even function. So what that means is if I change the angle to a negative angle, that just doesn't change the horizontal displacement. But even when I say that out loud, it's kind of that's it, right? That is the proof. That is the proof. And here's the picture of it. There we go. That's the picture of it, right? So if I change my angle from a positive value to a negative value, that doesn't change the horizontal displacement. So there you go. By definition, that means that cosine negative theta is equal to cosine theta, or not by definition, by the picture. And then now, by definition, this means cosine is an even function. There you go. Pretty nifty, huh? Not too bad. Why is this helpful? Well, evenness and oddness comes up in a lot of contexts, and it can cut your work in half, or it can cut your work to zero entirely. You'll see it a lot in Calc 1 and Calc 2, actually. So do get comfortable with even and odd functions. But let's try an example here, a simple example. See if you can do this using even and oddness properties instead of just using only the unit circle. So think about it for a minute. Now try to say something out loud to yourself. Anything at all about what you're seeing here, what you're reading, and how you would approach the problem. All right, now try to work it out yourself. See if you can use even and oddness to find the answer to these things, these values. Okay, now let's do it together. So if I'm going to use even and oddness, I remember that sine is an odd function. What does an odd function mean? It means this. Sine of negative 45 degrees is going to be negative sine of 45 degrees. Because if I change the sign of the input, it changes the sign of the output. All right, but what's sine of 45 degrees? Unit circle. 45 degrees, 45-90 triangle. It's root 2 over 2, so this becomes negative root 2 over 2. Done. There we go. So now we didn't even need to contemplate going in reverse, right? Although we could. You could easily just look at negative 45 degrees and go that way and get the same result. There's more than one way to do it. Okay, what about cosine of negative pi? That one, cosine is an even function. So cosine of negative pi is the same as cosine of pi But that we know is just going to be -1, right? Over there, you'll have -1. Okay, now tangent -37 pi over 4. Let's see, tangent is an odd function, so we know that we're going to have negative tangent 37 pi over 4, right? But then, what does 37 pi over 4 look like? We got to mod out by 2 pi. Think of it as a multiple of pi and get rid of all of the repeated rotations, all the repeated revolutions. So let me do some side work here. 37 over 4 pi. See, 37 divided by 4 is how much? See, 36, so 9 1/4 pies. 9 1/4 pies. So on the unit circle, I'm going to go around and around for 9 pies and then another 1/4 pi. So because it's 9, we're going to do a bunch of full rotations and then another pi and then a 1/4 pi. So like you'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, and then another 1/4. So you'll be down here. All right. That's what's the tangent of that line? Oh, I can see it in the picture, right? The tangent of that line, what's the slope of that line? The slope, oops, the slope is going to be 1. The slope is going to be 1. So this is going to become -1. There you go. All right. Boom. There we go. Negative tangent pi over 4. -1. And that's it. So that's how even and oddness can help you for evaluating these functions. But what's nice about this is if you're comfortable with the way that we've been evaluating these functions using the unit circle, even an oddness doesn't save you too much work. But what you're going to find out when you get to Calc 1 and Calc 2 is that it literally will cut your work in half or cut it down to nothing because of the way that these functions behave when you integrate them over a symmetric interval. But that's for a later class. So now you can go play, try these out on the homework, ask questions if you have any, but that's it for this section. So I'll say thank you again for listening. I'm glad this one wasn't as long, and I'll see you next time.